Hi guys. Okay, so in this video, we will cover chapter 7 of chemical bonding from the book Chemistry, second edition in OpenStax. Okay, so in this video, we will discuss the covalent bonds and we will use the average covalent bond energies to calculate the enthalpy of the reactions. So first of all, what are the bonds? And then we will discuss what is the bond energy and how are the bonds formed and the characteristics of the bonds. So first of all, if you look at how did the concept of bonds even come about? So if you look at carbon, okay, carbon, when it's in a graphite state, it is very soft. It is very soft. It kind of just a little bit of pressure and it just rolls over. But the diamond is the hardest substance known. So why both these substances, graphite and diamond, are made up of one type of atom, which is carbon, but they have entirely different properties. Similarly, look at silicon and carbon. Both of them belong to the fourth group, 4A. Okay, so in group 4A, silicon and carbon, when they combine with oxygen, one gives silicon dioxide, which is a solid, and you can see. But the other one gives a gas, which is invisible, and you can't even see it. So we have one forming a very visible solid and is actually very widely known also, silicon dioxide, whereas carbon dioxide is a gas and we can't see it. So why is that two different substances are formed when oxygen, the same atom, is reacting with both of them? So again, it has to do something to do with the bonds. Okay, now what is bond? What is the bond? How do you define a bond? A bond is a force that holds the group of atoms together to make them function as one unit. Okay, it could be like one molecule or even like a crystalline arrangement and those things. Okay, next is, these are the bonds that are responsible for the physical and the chemical characteristics of the substances. The physical properties, for example, are such as the melting point of a substance, the boiling point of a substance, the freezing point of a substance, the density of the substance, how a substance looks and feels, all those basic things, the specific heat, the solubility of the substance, all that depends on the bonds. Next is the chemical properties. How does a substance react? How does a substance react with either oxygen or water or acids or bases and those things? So the reactions, the chemical reactivity of the substance is also depending upon the nature of the bonds a substance has. Now, that's the very basic things about the bonds. Now let's look at a little bit in detail, how are the bonds formed? So first of all, the bonds, let's look at a situation where two atoms of hydrogen. Now remember that bonds internally, they want to have the electronic, every atom internally wants to have the electronic configuration like the nearest noble gas. So that is the driving force where they either give away the electrons or they take electrons or they share electrons. So here we have hydrogen with one electron, right? So this is one electron of hydrogen. So it's 1s1 here and 1s1 here. But ideally, they prefer to look like helium. So they would have a fulfilled s orbitals, s2, right? So they are looking to pair. Remember, bonding means pairing, making connection, making bonds. Okay, so here you have two atoms of hydrogen. Now look at this energy profile in this diagram. On this coordinate, we have the energy kilojoules and per mole. And on this axis, we have the internuclear distance, the distance between the two nucleus. And this is measured in nanometer. Nanometer here, kilojoules per mole is the energy on the other side. Okay, now look at this. Here is 0. 0 stands no energy, right? And all the numbers below 0 will obviously be negative, and the numbers that are above 0 will be positive numbers. Okay, now if these are the two atoms of hydrogen, if they come too close to each other, what is going to happen? They are obviously looking to bond, but what is going to happen if they come too close to each other? Then if they come too close, so this too close causes repulsion. Negative and negative, remember, in the end, they are electron clouds. So repulsion. So electron of one and then the electron of other, they repel. And so negative and negative, they repel each other, and that causes them to drift apart. Okay, so they move away. The moment they come close, the moment they come close, so this, if they are too close, then they move apart. If they are too close, then they cannot bond. They will be like hitting each other, and they part ways. Okay. Now, on the other hand, if they are, and that means it's a positive, that means too much energy, very high energy in this state is very high energy. Okay. Next is, if these two atoms of hydrogen and hydrogen are too far apart. So in this case, this is a scenario where they are too far away. If they are too far away, that means there is no interaction. No interaction. So again, the energy is very high. So that is why the energy is positive and it is above zero. So no interaction, energy is very high. Okay, so energy is E. Okay, now in order to come close, they have to come at a certain distance. Okay, and again here in this case, like I said, no interaction, nothing, even if they so in the top scenario where the energy is very high, there is no possibility of forming a bond. In order for them to form a bond, they have to come close, and they have to come not very close, but at a certain optimal distance. So they have to give away their energy. So in this is a scenario where the electrons are giving away their energies and they are coming close. So electrons, the atoms are approaching, so the energy decreases. So let me write this down here. Atoms approaching, and that means the energy is going down, or they are giving away the energy. So if you look at it, it is below zero and it is in the negative, but still they are far away. But atoms still far away. So again, even if they're far away, but their energies are lower, they can form the bond. The only way they can form the bond is when the nucleus of one talks to the electrons of the other, and the electrons of the other are attracted by the nucleus of the other. So this way, this is what maintains, that connection. So that optimal distance when they come close to each other, where the nucleus starts getting involved, is 0.074 nanometer. This is the internuclear distance, and this is also called a bond length. The bond length, the length at which they are, placed in such a way that they are mutually attracted to each other. And now they have given away substantial amount of energy, but some amount of energy is given to the surroundings, but some of it remains within the molecule, because now you have to maintain that bond length, that optimal distance, that attraction between the nucleus and the electrons, right? So where is that energy? Energy is needed to maintain that, that structure, that bond, that at H and H, that single bond, and that energy gets stored, and this energy is negative 4.58 kilojoules per mole. So this is the system in this state is at the minimal energy state. So here is the minimal energy. Okay, in the minimal energy state. And so zero energy basically means no attraction. Okay, but the negative energy, as you go down, the negative, if it says attraction, the energy becomes negative. And the more the negative energy is, the more the attraction, that means the bond is strong. Now let's look at once the atoms have come close enough that the nucleus of one let me write this down somewhere, that the nucleus, when the nucleus of one hydrogen attracts the electrons of other hydrogen, then bond is formed. Okay. And that always happens at the lowest energy state, at the minimal energy state, that happens. Okay, so that's now, once the bond is formed, it has to be maintained. It has to be kept, solid and strong, so that's what gives the identity to the substances. Okay, so like you see, that's we see something is soft, something is hard, something is visible, something is invisible, something is solid, something is gas, something has a certain boiling point, melting point, certain type of reactivity. All that depends that setup of that optimal distance and that attraction between the two atoms need to be maintained. Okay, so now we look at the strength of the bonds. Now there are certain tables in your book, or these values are going to be given to you. So you are going to refer to these tables for all the problems that you're doing. You're going to refer to these tables in the book or in the appendix. And on the exams, like I said, these values will be given. So it's not like you have to memorize, but just try to understand that the bond length for a single bond is more, double bond is in between, and the triple bond is the lowest. So we see that the triple bond, the atoms are more like very close, are more closer to each other versus this double bond and the single bond. Secondly, look at the bond strength. Obviously, if the atoms are very close to each other, then what's the deal then? If they are very close to each other, that means there's something. These three bonds, a lot of energy is there in them. These three bonds have a lot of energy. So the bond energy of a triple bond is higher than the bond energy of a double bond, and the bond energy of the single bond is the least. In other words, the strength of the triple bond. So this is the triple bond is going to be the strongest. And in comparison, this is less strong, or least strong, you can say, least. I mean, single bonds are also strong, but so everything is comparative. So strongest is the triple bond, and the least strong is the single bond, and the double bond forms in between the two. Okay, so that's the thing. So keep this in mind, that the stronger the bond, the less is the bond length. So let me just do this. Bond type, the strength of the bond, it depends on the bond energy and bond strength of the covalent bond. Sorry, here, let me put this here. Strength of the covalent bond is equal to, this is the BS. So the BS, the bond strength, is inversely related to bond length. The longer the bond length, the weaker the bond strength is. Next is the bond strength is directly proportional to bond energy. So the stronger the bond, the more the energy there is in it. So this is the relationship you need to keep in mind, the relationship between bond strength, bond energy, and the bond length. Okay. Next is, we are now going to look at the covalent bonding and the, so this is how the covalent bonds are formed. Now keep a few things in mind, that the amount of energy that is needed to make a bond, it is the same amount of energy that is needed to break the bond. So bond making and bond breaking involves the exact same amount of energy. So look at it here. You have here one atom of hydrogen and another atom of hydrogen, right? Very high energy state. This is in a gaseous state, very high energy state. They give away 436 kilojoules of energy in order to form H2. Okay, they have to give away 436 kilojoules of energy. Now, if you have a bond, if you have hydrogen and hydrogen already bonded together, in a single bond, then you need to give 436 kilojoules of energy to break that single bond so that 2 atoms of hydrogen could be released. So keep this in mind that on one end, this reaction is exothermic. So bond making is exothermic and bond breaking is endothermic. So the amount of energy is the same, both the sides. The only difference is delta H will be a negative number, and here delta H is a positive number. So that's the only difference. Okay, now let's look at some of the scenarios here. So energy that is needed to make the bonds is the same amount of energy that is needed to break the bonds. So making and breaking takes it on. Let's see first a few examples here. So let's look at this example. Example 1, and here we have CH4, which is a methane. Okay, so now it's very important in this case that you make the right Lewis structures. So the Lewis structure in this case is CH4 looks like this. Okay, now in this CH4, you need to give to methane 1652 kilojoules of heat. 1652 kilojoules of heat needs to be given. So only then this molecule is going to break up into 1 carbon, okay, and it is going to release 4 atoms of hydrogen. Okay, so this is the energy that is needed to break the bonds. Now, on the other hand, if you have 1 atom of carbon and you have 4 atoms of hydrogen, then to these guys, you are going to, these guys are going to combine to give a CH4, and they're going to release 1652 kilojoules of heat. So here in this case, heat is released. And in this case, the energy is absorbed. And it's the same amount of energy that is absorbed is the same amount of energy that is released. And it's always very specific to the kinds of bonds there are. So we are basically looking at breaking 4 bonds here and making 4 bonds here. Okay. Now, from here, from this is for the whole reaction, right? But now we can find the energy of stabilization of each CH bond. So we, from here, from this, we can determine the energy, and that is equal to the bond energy, basically, bond energy of each CH4 bond. Okay, so we can find out, how much is this, how much is this, how much is this, and how much is this. Okay, so these 4 bonds we can find. How? So we take 1, 6, 5, 2, divide that by 4, and that gives you 413 kilojoules per mole of heat of the CH bond. So this is how they calculate the bonds of individual, parts in a molecule. Okay. So 1652 divided by 4, and that gives you 413 kilojoules per mole. All right. Now let us say you have some examples here. For example, you have, this was the first one, and now let's look at the second example. Example second. Now here, you have CH3Cl, okay? And using this, find the energy of carbon and chlorine bond. So we know the CH bond. From here, we know the CH bond. The CH bond energy is this. The CH bond energy is this, 413 kilojoules per mole. Then find for CCl. Then how do you do this? So here, what is given to you? This is given 1 of carbon in a gaseous form, okay, reacting with 3 of hydrogens, also in the gaseous form, reacting it, 1 atom of chlorine in the gaseous form, and this gives you CH3Cl in the gaseous form, and it is going to release 1578 kilojoules per mole. Okay, so this piece is going to be given to you. This is given. The reaction along with the amount of energy that is released. So let's now just do this here now. So we have in this CH3. So there are 3 of the CH bonds, and there is 1 of CCl bond. Okay, and so that totals 1578. So let's write this here. So 1 carbon and chlorine bond plus so that's the bond energy of 1 carbon and chlorine bond plus the bond energy of 3 carbon and hydrogen, bonds, and this whole thing is equal to 1578 kilojoules per mole, for 1 mole. Okay, now here we have 1 CCl, this is the one we need to find out, okay, plus 3 multiplied by carbon hydrogen bond was 413 kilojoules per mole. So 3 times 413 kilojoules per mole. Remember that this is 3 is the 3 moles. Okay, so 3 moles, this is 1 mole. Okay, is equal to 1578 kilojoules per mole. Okay, now 1 CCl is equal to 1578 kilojoules per mole minus the 3 times 413 is 1239 kilojoules per mole, and this gives you 339 kilojoules per mole. Okay, so the value of carbon and chlorine bond is 339 kilojoules per mole. So you see here that we can determine for some of the molecules, some of the bonds we can determine, the other ones we need to find out by these methods. All right, so this is one piece. Now let's look at another example. Another example is, let's see, this is the example number 3. Okay, here you are given CH4. So this is a reaction that is given, CH4 methane in the gaseous form is reacting with 2 of the Cl2s in the gaseous form and 2 of F2s in the gaseous form. Okay, then give what is formed. What is formed here is CF2 Cl2 in the gaseous form plus 2 of HF in the gaseous form, okay, plus 2 of HCl in the gaseous form. Okay, so the question is now that find the total energy for this reaction released. So what is the total energy? What is the value of delta H for this reaction, this whole reaction? Okay, now there is a formula that we are going to use, and the formula is that bond energy for a reaction, delta H for a reaction is, that is the bond energy per mole, kilojoules per mole. That is the total number of moles, okay, times. Now, D also stands for, D stands for the bond dissociation energy. So bonds broken, okay, bonds broken means these are going to be the reactants minus the sum total of the number of moles times the D of the bonds formed. Okay, bonds formed. Let's just put this here. Just give me 1 minute. D bonds formed. Okay, so this is one way of writing it. Commonly, you've seen it, but there's another way of putting the whole thing. So delta H, let's put this in red color. Delta H of this reaction is equal to the sum total of the number of bonds times the number of moles times the bond energy of the reactants minus the sum total of the number of moles of the bond and the bond times the bond energy of the products. So generally it is the products minus the reactants, but this one is special. It's reactants minus the products. All right. So now let's look at it here. What are we given? We will be looking at the table, right? We are going to be looking at the table to get some of the values, and these will be given to you. So let's look at what will be given. We will be given some values. So CH. So we will be given the bonds and the bond energy that's associated with that bond. So for the CH, carbon and hydrogen bond, the bond energy is 413 kilojoules per mole, and we calculated that also. Okay, that's one piece. Next is the Cl2, chlorine-chlorine bond. So chlorine-chlorine bond will be 239 kilojoules per mole. Okay, this is given. Next is the fluorine-fluorine energy. Fluorine-fluorine energy is again given 154 kilojoules per mole. Okay, now next is the carbon and fluorine bond. So again, from the tables, you will have to get these. So carbon and fluorine bonds is 485 kilojoules per mole. This is again given. Next is carbon and chlorine bond. Carbon and chlorine bond is 339 kilojoules per mole. Okay. Next is hydrogen and fluorine, HF. The energy of this is 565 kilojoules per mole. Okay. Next is hydrogen and chlorine. And here you have 427 kilojoules per mole. Okay. Now let's look at this. Here, first of all, we have CH4. So CH4 is we will follow this one. Let's do this. So delta H for this reaction is equal to the energy that is needed to break the bond. So the total number of the times the bond energy, moles times the bond energy of the reactants minus the sum total of the number of moles times the bond energy of the products. Okay, now let's do this. Here we have CH4. So let's draw these molecules here, CH4. So we are looking at four of the CHs, here. Next, we are given the 2Cl2. So we are given plus 2Cl and Cl bond. Okay. Next, let's put this here, fluorine plus 2 of the fluorine dash fluorine. So that's a single bond, both of them. And now comes the CF2Cl2. So what is the C F2. So there are two carbon and fluorine bonds and two carbon and chlorine bonds. So keep that in mind. So this is one scenario, CF2Cl2 and HF and HCl. So plus, then there is, sorry, 2 HF and 2 HCl. So 2 hydrogen and fluorine bond plus 2 hydrogen and chlorine bond. Okay, so now the reactants are, these are the reactants. So we will combine the energy of all these, get number here, then let's get the number of these. So that is, these are the reactants, and let's get the bond energy of this side and then the bond energy of this side, and then just subtract. Okay, so let's do this here. Okay, so we have 4, so sum total, right? So 4 number of moles. So 4 moles of CH bond. So how do I put this here? Let's do this here. 4 moles of CH bonds, sorry, C-H bond. Okay, and that is equal to 4 times 413 kilojoules per mole. Okay, and that comes out to be 1652 kilojoules. Remember, those moles cancel out. Next is, we have the 2 moles of chlorine ClCl bond. So so it's obvious it's bond, right? So ClCl. Okay, so here we have 2 times the ClCl given from the table is 239. So 239 kilojoules per mole. Okay, so let's put this also put correctly, kilojoules per mole. Okay, and this comes out to be 478 kilojoules. Next is, we have 2 moles of fluorine and fluorine, 2 moles of fluorine and fluorine, 2F2. So that is 2 times the fluorine is 154 kilojoules per mole. So 154 kilojoules per mole. Okay, so now here you are just going to add 1652 plus 478, and then this one is also coming out to be, let me just put it here, this one is equal to 2 times 154 is 308 kilojoules. So when you add these, you get 2438 kilojoules. So this is the value on the reactant side, the total energy that is needed to break the bonds. This is the total energy needed to break the bonds. That is on the reactant sides. Break the bonds on reactant side. Okay. So reactants are R and products are P. Okay, next, let's look at the scenario on this side also. So we don't have to, let me just put this here, one big line. Okay, here we have now the 2 moles of CF. So we have 2 moles of carbon and fluorine, and we have 2 moles of carbon and chlorine. Okay, so carbon and fluorine, so is 2 times the carbon fluorine is 485. So 2 times 485 kilojoules per mole, and that comes out to be 970 kilojoules. Okay, and 2 moles of carbon chlorine comes out to be 2 times 339 kilojoules per mole. Okay, and this is equal to 678 kilojoules. Okay, so this molecule right here is this one, is this thing here. Carbon fluorine, 2 of them, and 2 of the carbon chlorines. And here we, because of that, now we have 970 and 678 in one molecule. Next is we have another piece on the product side is the 2 moles of HF and 2 moles of HCl. Okay, 2 moles of HF is 2 times 565, sorry, 2 times 565 kilojoules per mole. And the other one is 2 moles of HCl is 2 times 427 kilojoules per mole. So just remember that these are coming from these tables, 427 and 565. It's given to you. So you just have to plug in those numbers. So now we got these. So 2 times 565 is equal to 1130 kilojoules, and 2 times 427 is 854 kilojoules. Okay, and now you are going to add these. Add. Okay, so when you add, it becomes 3632 kilojoules. So this is the total energy needed to make the bonds on the product side. Okay, now we're not done yet. We will have now to take these 2 numbers and get it for the whole reaction. So the value of delta H is delta H for this reaction is equal to the bond, dissociation energy. So it's breaking. So, or I prefer to write it like this: bond energy of the reactants minus the bond energies of the products. So these are the right, formulas. So anyways, so we now have 2, 4, 3, 8. Let me use another pen. 2, 4, 3, 8. 2, 4, 3, 8 kilojoules. That's the energy we calculated from the top. And the next one is minus 3632 kilojoules of energy. So this is the value of delta H for the reaction. Okay, so when you subtract it, small number minus the big number, the sign is of a big number. So it is negative 1194 kilojoules. So this is for the whole reaction, bond energy. Okay, and since it is negative, that means this is exothermic. That means the energy is released when 1 mole of CF2Cl2 is formed. Okay, so these type of questions, as I said, that these bond energy values will be given to you. The main thing is drawing the right Lewis structure. Drawing the right Lewis structure. If the Lewis structures are wrong, then you can get this whole thing right. So this is the most important thing. Let's just put this here in color and just make sure that you draw the right Lewis structure so that you have the right values. Okay, and make sure you balancing also is important. So balancing, so make sure that balancing, if the balancing is not done right, then also these type of reactions don't, this type of problems don't. The rest is just addition. Okay, so that finishes this section. And if you have any questions, you can always ask. Okay, thank you for watching. Bye-bye.